Hey guys, before I get into everything, I just want to say that Virtual Robot Simulator, who I work with, is doing a tournament for the 24 hours following the release of the game, where you guys can code autonomous on their website to compete in an epic tournament. Also, if you ever want to reference these slides or contact me to help with mentorship or access the Virtual Robot Simulator, you can just take a photo there, and that's all the links as well as my contact information, because I'm an Illinois Robot mentor, and I also mentor a bunch of teams throughout the nation. So let's get into this. First, I'm going to cover how to do different common FTC sensors, then robot vision with the basic implementation of TensorFlow and OpenCV, followed by the different autonomous navigation systems your team can use and how to implement them, and finally a Q&A. So to get started, let's cover how to use common FTC sensors. So as you know, when you're doing your programming, you always have to configure your robot with these different sensors. This allows your program to actually access the sensors because after you plug them into the ports, you have to name them so you can access them in the future. So to configure your color sensor, you would connect it to the I2C ports of your hub, and then have it configured as a rev color-range sensor. And you would obviously name it. Here's the name sensor color range. To actually program it, you would want to import the color sensor library, create a variable of type color sensor based on this class you've imported above here. And then you can use the .red, .green, and .blue, as well as .alpha and .arbg to read the values of this color sensor. So this could be useful for example, let's imagine I have a color sensor inside of a claw. If I want the robot to go forward until the robot has an element in its claw, I could use the color sensor to be like, if the element's white, once the color sensor has a alpha value, which is the whiteness the color sensor is reading, it'll know to close the claw so I can pick up that element in autonomous mode. This could also be useful if a color sensor is underneath your robot, and you want the robot to move forward until the robot sees like a white line, a blue line. In this example, so while the color sensor's alpha value is less than 20, the robot continues going forward then until it has an alpha value that's greater than 20 in this while loop. And the alpha value is the whiteness of the color sensor. So once the color sensor is over a white line on the field, then the robot can stop and do something else and behave accordingly. This could be used with blue, red, any of the colors described before too, depending on the element color you need to see. Another very useful sensor is the touch sensor. So touch sensors connect to your hub's digital I/O ports and is configured as type touch sensor. You would import the touch sensor class above here using this command. Then you would have create a variable of type touch sensor, and finally you connect it to your hardware map based on what you named the touch sensor there. In this example, it would be named touch_sensor. And here, here's an example where if you want to drive until the touch sensor button is pressed or 5 seconds passes, here it's doing while the get runtime, so it's actually reading the runtime of your match is less than 5 and touch sensor is not pressed, it's going to run this code. So touch is pressed returns true when the sensor is pressed, it returns false otherwise. Another important use of this touch sensor, besides just being able to touch a full sensor on your robot, is it can be used as something called a limit switch. So what a limit switch is let's imagine I have my claw of my robot, and I want to be able to detect when my claw is all the way down to reset its encoder value. Encoders are how you track its position, but over time, they kind of get messed up, and you need to be able to keep your claw in the correct positions. So during driver control, whenever the claw hits the bottom, you could have it connect to a touch sensor, hit that, and then it'll know to reset that encoder value. This can also be used for features like once the claw is all the way down and the touch sensor is activated, the claw opens up. You can even make it so if the robot, the claw is open and something hits a touch sensor inside of it, the claw knows it has an element and can automatically close based on your programming to help drivers or to help during autonomous. Some other cool sensor usage your team can incorporate is here. My old team used a voltage reading module to connect it to the battery. So we took the battery, connected it to this, and then connected it to our robot. And this lets us actually see the value of the voltage live on the robot, which is pretty awesome looking, and it lets you easily see the voltage throughout your match and what's draining more power. We also use these switches down here. So as you know, you're starting on the red side or the blue side of the field, and they're firstly mirror images, so you need at least 2 programs. But then you probably are going to want even more for different strategies, like what your alliance partner's doing and what you're doing. You're going to talk about this right before the match, so you need a lot of different programs to do all of these different strategies. So some teams have all these programs just on their phone, like red, this position, this strategy, red, this position, this strategy. But unfortunately, in my experience at least, it's pretty easy to sometimes make a mistake, hit the wrong program, and have your robot behave in unexpected ways. One way my team got around this is we had these switches down here. So this switch has red on this side, and if you flip it the other way, that's considered blue. And here it's like the storage strategy, and on the other side was a duck carousel strategy. That's what we named them. So to actually read the values of these switches, we connected them to the digital I/O ports of our hub. Then we read there from the digital channel, that's the type of the switch. Then we used the hardware map to connect them. This switch was named SWPOS, switch position. And then here you can just use the get state command to actually read that switch's state. And we use telemetry to show its position and which program we'd be running based on the position of the switches. This way, before the match, we talked with the other team and we just flicked our switches and made sure they were all perfect before running, so we never had errors with selecting the wrong program. Another important thing you'll have to do this year is connect a webcam. It's very easy to connect a webcam to your robot. You just plug it right into the USB port of your hub, and your webcam's right here labeled, so it's very easy to load up. So for this season, there's a lot of different options for robot vision. I'm going to be covering the basic implementation of TensorFlow this year, as well as OpenCV. So TensorFlow is a great option if your team doesn't have much experience with robot vision. Pretty much, first is going to create a TF-Lite file for you. This TF-Lite file allows your robot to actually be able to see an image and detect exactly what's, if any game elements from first are in that image and where they are on the field relative to your robot. So first we'll do all the work to train this epic library for you doing this awesome process. And then we can use these TensorFlow Lite files there to get an output like this with our camera automatically. So in order to implement TensorFlow, you can get a Vuforia license here at this link. So Vuforia works with TensorFlow to actually give you the coordinates of game elements that you can detect on the field. This way, if I'm on the field, I'm looking through my camera, I can get like the coordinates of a sphere is 5 inches to my left. And this way you can have your robot move to go and pick up that sphere based on knowing its actual position relative to your robot. So to set this up, you can easily open the TensorFlow example in the FTC SDK. If you're on Java or Android Studio, it's named Concept TensorFlow Object Detection. And you want to make sure to undisable the app mode. A lot of teams are like, it's not working. It's because it's disabled automatically. Undisable the app mode. And finally, you only need to adjust a few lines of code to actually fit your season. So there's a whole tutorial here. If you just take that link for the slides, you can open this up and go and find that tutorial. But pretty much, here's the TF-Lite file from the Freight Frenzy season. So you have to set that here as your asset. And you also have to set the labels for each of the elements. So this season there was balls, cubes, ducks, and other markers. And this way you can actually find and identify these elements. So these FTC TF-Lite thing will be released a bit into the season. So while you're experimenting at the start, you can use an old year's TF-Lite file. And this lets you still get progress in programming because often first uses similar game elements. Like they've used that ball and cube for many games. Let's imagine that I just want to find the color green because I have a game element that's green and nothing else on the field is green. What I can do is set everything that's not green to black, and only green elements are going to be white. And this creates a black and white image with just green elements being highlighted in white. So what we're going to do is you open your camera. Let me show you exactly how this works. So here my team had to know which position our marker was in, and our marker was bright green. And we had these 3 different rectangles on the field. So we wanted to know which of these positions with our camera was in it, like which of these rectangles was the marker inside of. And based on this, our robot behaved differently. So to actually set this up by detecting where your elements is, you're going to use Easy OpenCV, which lets you use this software called OpenCV with the FTC SDK. So first, it's provided by Easy OpenCV. And then you want to use upper and lower bounds of the color range to actually see. So here would be our dark green and light green. Because we have a bit of a range because maybe your field has a light over it. Maybe it's really dark over your field during game day. You can't just set one exact color because then any change in lighting, your robot's not going to work. So here you set some dark green, some light green, so depending on lighting, you're good. And these values are HSV values. So has anyone heard of RGB, red, green, blue? Yeah. So hue saturation value is pretty similar. It's just like a different way you can represent all the color values. So it also just lets you make them whiter or darker with the value, which is brightness. So it stands for hue, saturation, brightness. And you can easily represent all these values with just 3 numbers. And then down here, we have to, hue, saturation, value. Down here, we create the areas we're going to check because you have to set the coordinates of each of these rectangles. So here's like the left corner, the right corner, the bottom 2 corners. It actually creates those different ranges on our camera that we're going to be checking if the element is inside of. And then we have a nice little variable here for the position of our element, which currently we don't know, so it's just set to 0. Then we're going to process our image. So what we do is this is going to run for each of our frames, which is just what the camera is seeing. it's going to convert the image into hue saturation values. What this means is it's taking every pixel and getting its HSV value. So it's kind of like if we took every pixel and got its RGB value based on the color. It's just like that, but with HSV, which is just a different format. Then what we're going to do is just make it so all the colors that are not in our lower to upper green range turn black, and just our green colors are white now. So now we have a black and white image with just the green turned into white and filtered out that way. Then what we're going to do is this is going to return the edited frame, but right here is where the magic happens. So this just makes it so on your actual phone, it's going to show the little rectangles so you can know where they are. And this just helps you edit your code, find errors. This is helping, since it actually displays the rectangle on the screen, I can see where it was and adjust it based on where the camera was to make sure it was in the right area to detect our game element. So here's where it's actually going to process that input and return. So pretty much, to process it before this final end here, it's going, there we go. And it won't let me advance. Great. So here, we go to each of these values, and it's finding the mean value of it. What this means is it's taking all these values, which are either black or white, and they have different intensities. It's finding the mean value of whiteness in each of the rectangles. So obviously, if the rectangle has the game elements in it, it's going to have a lot more white pixels because they all turned white. So it's going to have a much higher mean value than the other two sections. So what I do is I just use a loop to iterate through these sections, and whichever one has the greatest value of whiteness in it is going to be where our game element is, and that's how I know the element position. So now I'm going to cover some different autonomous navigation systems you guys can use this year throughout your season. So firstly, what is odometry? Odometry is the use of sensors to determine a robot's position. Dead wheels are unpowered omni wheels underneath your robot and have rotary encoders attached to them to track the distance traveled by your robot. So here are some examples of dead wheels. These are not powering your robot, they're just moving along as your robot moves. And odometry can allow for localization, the autonomous tracking of the position of your robot, and is essential for advanced autonomouses. So often teams, when they first get into FTC, just use time-based movement where the robot just goes forward for 5 seconds, but what if another robot bumps into you or something? Then you're doomed, because your robot's been bumped into, it goes haywire. Here, the robot will know, oh no, I'm off course, and actually be able to correct itself. So the first type of odometry possible is just drive wheel odometry. Here, the benefits are that no dead wheels are needed, so no space is taken up on your drivetrain. It just simply uses the encoders of each of your motors to actually track the robot's position. So the negatives, though, are that the mecanum wheels do experience slip as the robot moves, especially side to side, and relying on their motors and encoders can decrease position accuracy, especially if the robot's pushed in like a way it might not be able to accurately track that change in position. Another option would be 2 dead wheel odometry, where you just use 2 dead wheels, one to track your movement in the Y direction, one to track your movement in your X direction. It's pretty simple to program because one's Y, one's X. The only negative is that you need to use the IMU to determine your orientation, and IMU communicates through I2C, which is pretty slow, which could delay your position loops, which could reduce your accuracy, because this loop will be going throughout your whole program, constantly tracking your position. And if it has to wait for this IMU reading, it could actually decrease your accuracy throughout your movement. The best option for odometry would be the 3 dead wheel odometry system, where this can actually track your robot's movement in the X and Y plane, as well as the orientation of your robot. The benefit is that it's the most accurate, but the only negative is that you need 3 of these dead wheels here. So these are the different options. Obviously, the least parts is the least accurate, and the most accurate has the most parts. So how do we make odometry actually work in our programs? We have some different options. One of them is pure pursuit. So this calculates the robot velocity to reach a point from its current position. We enter in waypoints to create a line path for the robot to follow. Here, like I have points, and this path is created by connecting those points that I enter, different coordinates on the field. Then this pure pursuit places a circle around the robot and sees where it intersects that path and has the robot orient itself towards that intersection. Then it adjusts the velocity accordingly to follow this path. So here's like a visual representation of what it is with these look-ahead points that the robot's trying to follow. So here, let's imagine I put in some different coordinate points, and it creates a line connecting them, my waypoints, and then the robot has this imaginary circle around it where it finds this intersection of its circle around it and my points to follow this path that I've created. If you guys want to do pure pursuit, go to this link here, and it has a step-by-step tutorial on how to get that started with your robots this season. Another option you guys can do is Roadrunner. So Roadrunner, you give it the coordinates and an orientation if wanted at different points on the field. Then Roadrunner will generate the most efficient path for your robot to follow these points. What's the most efficient path look like? Well, it looks like a beautiful spline. That's what that nice curvy shape is called. So pretty much the robot's gonna be moving in all these different curves while spinning across the field, because that's normally the most efficient path between different points. Here's some instructions on how to get Roadrunner started with your robot. And finally, I also built my own odometry library that uses trigonometry instead of the highly advanced mathematics in these libraries. It's pretty good to have like a library that's trigonometry based, especially if you're starting, just to see how this odometry actually works with tracking your position. You can also edit any feature of the code because you can look at it and actually understand it. And finally, that's all right. And finally, I'm there to support teams if they have any issues with it, because currently, like Roadrunner and Pure Pursuit, people who made them are no longer there to support you. So if you have any issues, there's no one who's going to be able to help you. So if you guys are interested in doing my library too, you can contact me at therobotwhisperer31@gmail.com down there. Just take a photo of that, and I can help you get started. So does anybody have any questions?
Is there, like, what's the advantage of a TensorFlow system over like a very well built OpenCV?
Well, TensorFlow is easier for new teams to get started with because it's hard for a new team to make a very well built OpenCV. It's also just really simple to set up. You know, use TensorFlow, you can have the position, you can have the game element, the likelihood it's there. OpenCV is definitely more versatile though, because like I can like have robots align with different elements, and so yeah, I prefer OpenCV personally, but I know a lot of beginner teams prefer TensorFlow.
Is TensorFlow more accurate?
I don't know, I guess it depends on the different situation. TensorFlow is pretty accurate at recognizing the game elements. I like OpenCV just because you can really adjust it to exactly what you want to happen, but like, TensorFlow is very useful as well, just with Euphoria to get the coordinates and move to the elements really quickly.
I have a question. Is the link for the beginner slide is
Yeah, that's because their Wi-Fi kind of bans half the things I want to do. It bans sharing slideshows. That's fun,
but the second one works though.
I know the advanced one I was going to set up before, so it was already set up at my house, so that link was fine. I set up the beginner link here, and it's like Google Slides ban sharing on the network of Wi-Fi. So just email me, and I can send you. I actually teach virtual robot simulator classes, so I teach teams to code step by step on the virtual robot simulator. So if you contact me, I can send you the videos I teach in my classes as well, which I have hundreds of students taking my classes from around the world in different countries and everything. I'm mentoring a ton of teams now with that as well. So if you guys are interested, you can definitely contact me. I'll send you the curriculum, and I can send you all videos, and I'm going to be posting another class this season to catch teams up. I'm also hosting a 3D design class using Onshape to teach teams how to create their whole robot, assemble it together, and then also how to import it into the virtual robot simulator to program virtually as well as physically, hopefully in the future.
Thank you very much.
Any other questions? I guess I can cover some of Coyote, my localization library. So if anybody wants to try using that, definitely contact me and I can send you the code. But so pretty much how my thing worked, which is a little bit different, is we just use trigonometry to actually get the locations, and it's actually like not that difficult to understand. So all we do is we can take the right and left change, like in the odometry wheels, and just average their change. And we also take the change in this horizontal wheel in the center of our robot that tracks its position the other way. Then I just apply some really basic math here. I multiply out the change in the encoder positions by how far that change is, because if the wheel moves like 20 degrees, is that 2 inches for your robot? Is that 3 inches? So I have a basic calibration program teams run, and that sets that up. And then I just use some basic sine and cosine functions down here to see, based on our coordinates and the coordinates we want to go to, how far away is that in the x and y direction. And I also take the orientation of our robot. And then I just have the robot turn as it moves based on like the values of the angle the robot has to move to get to that position to actually get there. So this is some pretty basic math if you want to set up your own system, or you can contact me, I can send you this code and I can help you implement it this year. What I liked about this is it is incredibly easy to calibrate. You run a program that's like 5 lines of code, and it sees how far apart your wheels are, sees how far each movement is. And also, you can actually understand this if you read it and you know basic trigonometry. You can actually know what's happening behind your robot and adjust it accordingly. And finally, I'm there to support you. We're going to get this working for you guys this year. Any other questions?
She used that odometry system at Worlds, and they finished at 7th with the robot.
Like it's accurate, yay. You guys ready for another awesome season?
Thank you very much.
Thank you very much.
Thank you.
How long did it take Coyote Library?
I think I spent like 3 months during the summer before the season started, but I continued perfecting it throughout our season because obviously as you're coding your robot, you find new things you want to do. Like I had to implement some new methods to make it so it could work inside of loop statements too. So like, well, I had, one cool thing is I combined OpenCV with Coyote because there was this thing where we had to spin a duck off a carousel. And our team was the only team that could actually find this duck using OpenCV. We moved to the side, and we worked with Coyote to have the robot be able to continuously move to the side until it was within our center rectangle. We filtered for the yellowness of the duck. Our robot was able to stop and pretty accurately pick that up, which I was very proud of. And it was cool to like combine this odometry system with that. Another cool thing is I heard with Roadrunner, apparently it takes forever, like after you initialize for it to all compile, because like it compiles there. This compiles in like 2 seconds because it's just trigonometry, so that's really simple to set up. And you just pretty much put a bunch of coordinate points as you want your robot to move, and it just moves to those positions. No real setup. Any other questions about coding your robots this season, working with odometry, cameras, any other type of sensors?
Okay, well, 9 more minutes to stall.
I know, I'm trying to think. Yeah, wait, went slower last time. Oh boy.
Quick question, you mentioned the I2C port is slow, is the USB port, is that slow as well?
I don't know, I only ever used cameras at the start of the matches and like during that, and it was able to load fast enough. Like
I heard there's something out there, it's like Slam, that there's like a specialized wrapper for it and it goes through the USB port. I'm
Yeah, I
curious if
haven't
that's
heard of
fast.
that, I think the USB port's faster though, because teams do use cameras a ton during their matches.
Yeah, it depends, because I know on the control hubs, there are, I think there's a USB 2.0 standard port, and there are some 3.0s. So it just depends on which one you're using there for USB 2 or 3. Because some cameras do better on USB 3 that only support USB 3, and there's some that are lower spec, like the ones that are in the pictures, which is a 720p camera. Those ones could do 2 or 3, but they are able to be compatible with 3 because they're so low resolution.
I can also show you guys the virtual robot simulator. Unfortunately, because of the Wi-Fi things, Unity won't load to actually let you use the simulator, which is really sad. But you can easily go here and program your robots, and what's even cooler is you go to robot configuration, you can actually import a CAD model of your robot and set like where the motors are and where the sensors are, and actually program VRS with that CAD model of your robot. We're still working on improving this feature, but this lets you really work and like improve your robot even if you're still waiting on the mechanical team to actually construct it. Oh my goodness, it loaded this time. This is amazing. I've been trying to get this to load all day. This is fantastic. Wow. Wow. Okay, well watch this, guys. This is so exciting. So you can take programs, simply put them in, initialize, start program. Look at that. That's amazing. So pretty much you can run it like here. This robot has different motors in different positions. You can have it easily like shoot different elements using its flywheel, scoring goals. And I have a whole curriculum to teach everybody from starting phase, like how to actually program every part of your robot using Virtual Robot Simulator. And I teach classes on it, so if any of you are interested, hit me up.
So how much of the Java standard library is supported?
We don't support cameras yet or odometry, so that's a pretty big limitation. It's best for like learning the program and more basic robots. Technically, we're converting from like JavaScript to Java, and that's what creates a lot of the issues with supporting more libraries.
Actually, I got a question about VRS. So, like, how did it come to be? Because I know that a team in our league last year, like, was really heavily involved in VRS. It was Rest in Peace. And so, like, I'm wondering, like, how was it set up? Like, I just ratings.
I believe the director of Illinois FTC, Mr. Jonathan Wayland, he's here today, and I'm going to be talking with him about VRS. He's who spearheaded the initiative, and then a bunch of other kids. We all work with him to help develop the software. Rest in Peace was able to get it implemented in the curriculum of 5th grade schools, so they also do curriculum development for this. They use the block code to help teams do it with blocks in these elementary schools, which is really exciting. And you know, VRS has these tournaments, and we can work with these elementary schools to have them all compete to program these robots in tournaments. I'm trying to take charge of high school and middle school level curriculum development using the written language section of Virtual Robot Simulator, which is pretty exciting as well. We're just working to spread our curriculum, make sure anyone can access this knowledge to get started with FTC, because often, like, getting started programming is one of the hardest challenges, getting that all set up. So we're hoping to help teams with that. Also, what's good is even if you can't afford an FTC robot this year, you can still learn the same Java skills through actually applying what you're learning. Because a lot of coding classes, you never actually get to apply it. Just like, this is a for loop. Here you get to use the for loop to have the robot do different movements, make squares, get points, scoring points in this game. That's a real FTC game, just on the field here. It's all very fun.
When the kids are just learning to do the basic programming and they may not have a really good understanding around like how the bot should look, how the robot should look like. You guys have like at least a basic structure of
This
it.
is the automatic robot for this game. Every game we have a different automatic robot because,
Okay.
like this game, if we just gave you a claw bot, it wouldn't be very useful. So we give you a robot with like some flywheels and whatnot. It's only if you want to that you can import your own robots. Currently we're working on improving this feature to work with like Onshape, but right now you have to go through Fusion 360. And you can import your CAD model and it just works in the simulator.
But going from the things I do know is going from the CAD simulator to being on the actual field. So if you did create your own one in CAD and import it and then code it just to kind of get a visual scene because you're still trying to build the robot itself, but you know, all right, this is what's going to look like, how it is exactly going to be in CAD. When you do take the code from, when your robot's all complete and built, when you do take the code possibly from this and put it into the actual robot, there is going to be some things you do have to tweak, like movements and that kind of stuff, because here is like a virtual world, there's no friction or anything, but then the robot going onto the field, there is friction of the wheels and that kind of stuff, so you might need to, everything won't be perfect, but you might need, or it's going to be close, but not exactly perfect, so you might need to do some tweaking of the movements because there is friction. Yeah.
The main purpose of the software is like for especially new coders to learn how to program robots even while waiting on like the mechanical side of the team to build. And it does let you get a great visual representation of your robot in the field. You will probably need to adjust some of your code, especially because it does not support webcams. But you can like still experiment with webcams in real life too while waiting for your team to help build a robot.
Does it support custom classes or is it just functions from?
Fortunately not yet. I was like, can I teach classes? And then the classes kept throwing errors and they're like, oh, we don't support classes yet. I was pretty sad. But they are working on that. They're adding new features every day. Like now we get custom messages to tell you exactly what's wrong. So that's a pretty exciting new feature because otherwise it was pretty difficult to find any small spelling error in your code and fix it. But now it can tell you like which line is incorrect, which really helps teaching coding classes to help troubleshoot things.
Wait, so how does this IDE work?
So they take the JavaScript, they take this and they have to try to convert it to run the robot in Java. The blocks is actually really easy to get to work. Because you know blocks, it actually plugs it into Unity to run it. There's like 6 different coding languages. It is a very complicated thing, but it works and it's beautiful. But here, converting this text into Java, because we have to use the Java to run the robot, but it's actually JavaScript that runs the website, has to convert the Java to JavaScript.
Why don't you just embed JVM to JavaScript?
Well, maybe that's what they're doing. I'm more on the curriculum side of working with the simulator.
So you said the curriculum were available, email, do you like send us the files?
Yes, I can send you the thing for my next live classes for it, and then I also have some video sessions that I've been working on, just recording in my own time, to help people walk through it. Yeah, everybody, even if you're not here physically, my email is therobotwhisperer31@gmail.com, so contact me and I can help mentor your team and help you take some awesome virtual robot simulator courses.